Assalamu alaikum everyone. I hope all of you are well. I'm Muhammad Muzammil and this is part 2 of session 4 of your SAT math workshop. And let's just dive straight into what is basic geometry. Basic geometry is, by the name, as the name suggests, it's very easy, it's elementary, and by the end of this lesson hopefully we'll all learn tricks and tips to score fully on geometry questions on the SAT. Well, we only have 5 different types of questions. We have a lot of different geometry questions on the SAT, but they can all be put into 5 subcategories, which are lines and angles, triangles and polygons, and other polygons, congruent and similar figures, quadrilaterals and polygons, and circles. So these are 5 major topics that the SAT geometry section will cover, and they're pretty easy, they're pretty basic, and some of you might even find this lesson a bit of a review, but we'll be still going into a lot of essential detail so as to help you guys understand how to work problems on the SAT, geometry problems on the SAT. Moreover, this is a sort of a different lesson this time around. This is a different lesson in the sense that we'll have examples in the end. So you'll have to stick around till then for the examples on the SAT. So before further ado, we dive into our first type of problem, type 1, which is just lines and angles. And a bit of a review is that a line is simply a ray connecting 2 points in space. A ray is just a point. It's just a line that extends, but there is no end point to the line. So let me tell you. So if this line, a ray, starts from point A, there is no end point, so it is a ray. It is not a line. If there are 2 points in space, A and point B, then the ray connecting these 2 points is a line. So this is a pretty elementary review about what a line is. And now, what is an angle? Well, there are a lot of definitions out there for what an angle is, but we'll keep it pretty basic for the SAT so that we can get to the questions quickly. And an angle is just what is made after when 2 lines intersect each other. So these 2 lines have intersected each other, and they've created 4 angles as a result. This is an angle. This is an angle A. It is usually given by a hat, small hat. Angle B, angle C, and angle D. Okay. And here on, we can also see that the sum of angles about a point is always at 360 degree. We can take it as a rule for now. That the angles about a point, this is just some point O. This is some point O. And the angle D plus A, this essentially means that D plus A plus B plus C all equal 360 degrees. Okay, let's move on. Now, what are parallel lines and transversals? Parallel lines are lines that proceed in the same direction without ever intersecting each other. Basically, these 2 lines, line A and line B, are parallel. How do we know that? Because essentially we can see that first and foremost, we can see that A and B will continue on for all times to come, and they will never meet. A mathematical way or a graphical way to say the same thing is saying that these 2 lines will never. This is a very important point that I'm telling you right now, and we will excuse me, and we will learn more about the importance of this when we're talking about polygons and parallelograms and trapezoids, and then you'll understand the importance of this point that I'm telling you right now. And that is, if there is a line passing through 2 parallel lines, an indication or a test of being parallel is that these 2 angles will always be the same. And here we can see the same thing happening. How do we see the same thing happening? These 2 lines are parallel. Yes, this line cuts the C is called a transversal. It's called a transversal because it cuts two lines. And to see that whether they are parallel, we can employ this check that we talked about right now, and we see that these two angles are actually equal. And a few other angles are also important over here. And what do I mean by that? Which two angles are important? Which other angles are important? We can see right now these two angles are equal. Similarly, we'll use a different color. These two angles are always equal, and also different color again. These two angles are also equal. So now what we can pay a little more attention and give these angles names. Now this angle here, these two angles which are equal, this 48-degree angle and this 48-degree angle, these are vertically opposite, right? These are vertically opposite to each other. This is vertically opposite to this. So 48-degree wala angle is called a vertically opposite. These two angles are called vertically opposite. We can give them names as well. We can call them A and B. Then we can say that A and B are vertically opposite. Okay. Now another kind of another pair of equal angles are this 48 and this 48. Now if I call this angle C, then B and C are equal because an exterior angle is always equal to the opposite interior angle. Okay, I'll repeat what I just said. An exterior angle is just always equal to an opposite interior angle. Okay? So if you do not understand this, pause the video again. I've also summarized all of this over here in the next slide, but I wanted to tell you over here before we summarize it in the next slide. So these two angles are always equal as well, and we can correspondingly we can also see that these angles, this is an exterior angle and this is equal to the opposite interior angle. So this makes sense, right? Okay. Pause the video, give it a little thought, and it will make sense. It should make sense. Next, we can also use these two angles and study these two angles and analyze how angle, what should I call this? I should call this D, I should call this E. That D and E are also equal and they are vertically opposite. They're also vertically opposite, right? These are vertically opposite to each other. C and F, vertically opposite. I should complete the word here. C and F are also equal and they're also vertically opposite. Okay, so these two angles are equal, these two are angles, and we learned a little check over here that angles about a point are always 360. Now here's the point right here, and we can see for ourselves if that really is the case. So 132 plus 132 is what? Then 48 plus 48 is 96, and all of this we can see that it equals 360 degrees, and we can make a similar analysis for this point over here. So this is a very important concept, and I want you all to pause the video and go back if necessary and see that you understand this thoroughly. So next, I've just summarized all of this. That another important thing that I just missed out is that interior angles. I'll erase all of this for a little bit. This mark over here. So these two angles are interior angles, right? If I call these exterior angles, so correspondingly these are interior angles, and the sum of interior angles is always 180. I'll repeat what I just said. The sum of interior angles is always 180. So we can check C and E are interior angles, right? So C and E should be equal to 180. So that is what we know from our rule. And that is actually the case, not surprisingly, but it is actually the case. 132 plus a 48 is 180, in fact. So we can check this rule over here as well. These two are also if I call this if G, A and G are interior angles, and the sum of and their sum is equal to 180. So all of this we have summarized in the next slide. And vertically opposite angles are always equal. Yes, we did that. The sum of interior angles is always 180. We did that as well. Angles at one point on a single side of a line is supplementary. So this is a new name, like vertically opposite. So there's nothing to get confused about. It's just a new name. That what are supplementary angles? Supplementary angles are these two angles. Wait, I'll use a different color. These two angles are supplementary angles. Wait a second. 48 and 132. Correspondingly, 132, 48 over here are supplementary angles. What I mean to say is that if you have a single line and the angle, let's say A over here, and another angle B over here, then these two angles are supplementary in the sense that A plus B equals 180. Similarly, if I have some angle C over here and angle D over here, then D plus C are supplementary and their sum is equals to 180 degrees. And this actually makes sense, because if A plus B is 180 and C plus D is 182, so we studied before that the sum of angles about one point is equal to 360. So A plus B plus C plus D should be equal to 360, because we read that, and that is true because this is 180 and this is 180. So moving on, and this is again the same property that we talked about. An exterior angle and an opposite interior angle are equal. So this angle, an exterior angle, and this an opposite interior angle are always equal. Okay, next comes what is called perpendicular lines. So, and if perpendicular lines are pretty easy to talk about, because if you have a straight line and if you have another straight line such that they intersect at right angles. So if this is the right angle, 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 they intersect at right angles essentially. So then these two lines, I will call this line A and call this line B. A is perpendicular. This is a symbol SAT uses for perpendicularity. So perpendicular. Okay, these two lines are perpendicular to each other. So we learned over here that whenever two lines intersect, they create angles, and whenever they intersect at right angles, then these two lines are perpendicular. And if two lines are perpendicular to the same line, for example, what I mean to say is that if two lines are perpendicular to the same line, if this is a line and this is a line, and they're perpendicular to the same line, they're both, I'll call this A, I'll call this B. Oh, okay, sorry. I'll call this B, and I'll call this line over here C. We can see that A and B are perpendicular to C. Then A and B are parallel. See, this is the first time we're using this property, that if there are two lines and they're perpendicular to each other, and these two angles are the same, right? Like we talked about over here, these two angles were the same, and hence these two lines were perpendicular, right? So these two angles are the same, they're perpendicular to C. So A and B are parallel. And the symbols that SAT uses is this. A is parallel to B. Okay. Now that we know a lot about lines and angles, we can jump into another part of our SAT, another type of question that the SAT will ask you, which is about triangles and polygons. And this is again pretty elementary, but again sometimes it can take some time to work through problems about triangles and other polygons. But worry not, because we've got it covered. We've got some tricks up our sleeves, and I'll teach them to you right now. But before that, we just want to review what triangles really were. Triangles were figures that were drawn when you connect 3 points in space. If this is a point in space A, B, and C, and you connect these three, so the figure that you'll get is called a triangle. And some key things about a triangle is the interior angles of a triangle. This angle, these are all interior angles. These always add up to 180. These always add up to 180. Furthermore, we've got three different types of triangles. These are the scalene, the isosceles, and the equilateral triangle. And there is, yes, a lot of you might be thinking there is another type of triangle, and we'll talk about that in a bit. But these are the three main different types of triangles. So, what is an isosceles triangle? An isosceles triangle is just a triangle whose two sides are equal. If I call this side A and A, so A is equal to A. These two sides are equal, and henceforth, these two angles, I'll call them capital A. And these two angles, small a, are correspondingly also equal. So what that means to say is, for an isosceles triangle, two sides and two angles are equal. For an equilateral triangle, all three sides are equal. A, B, C, C, then A equals B equals C. Sorry, I should again capitalize this. A, B, C. And hence, moreover, all these angles are also equal. And here I want you to think about something. That if the interior angles are always equal to 180, and these three angles need to be equal for the triangle to be an equilateral triangle, then all of them must, and they'll always be a 60 degrees. So if you didn't follow what I just said, I wanted to pause the video and go back a little and think about what I just said. If all these three angles need to be equal, they can only be 60 degrees each because they have to add up to 180. And for a scalene triangle, none of the sides are equal. They are not equal, and none of the angles are equal as well. I should have capitalized that again. Okay, here comes our very, very favorite triangle. It's a right angle triangle. And if one of the sides in a triangle is 90 degrees, then the triangle is called a right angle triangle. Okay, right angle triangle. So on the SAT, you might be given two triangles that are special. And why are they special? Because they make our lives very, 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 very easy. So what are these two triangles? These are the 30, 60, 90 triangle, 30, 60, 90 triangle, and another one is a 45, 45, and a 90 triangle. So a few things that we must learn about the 30, 60, 90 triangle is just how to identify a 30, 60, 90 triangle at first glance. Okay. At a first glance, if you see a right angle triangle, pay attention to what I say right now. If at first glance you see a right angle triangle and you see that for any one side is 2 times the other side. If any one side is 2 times the other side, then the triangle is a 30, 60, 90 triangle. Simple. It is often very difficult, more difficult, won't call it very difficult, but it is more difficult to identify a √3 ratio to one of the sides. But it is very easy to identify that one side is twice the other. So if you see a right angle triangle in which one side is twice the other, you know that it is a 30, 60, 90 triangle. And then obviously you'll memorize this, that if one angle is twice this one, then the third will only be a √3 times x, whatever the length is will be √3 times that x. Okay. And here we've labeled the side as well. Then the side opposite, this is the side opposite the 30 degree angle, will just be x, whatever that is. If it is 2, okay, then 2. Then the side opposite the 90 degree angle will be 4, and then the side opposite the 60 degree angle will be 2√3. So we've studied the case. In the case that x equals 2. Okay, so I want you to pause the video again and see that you can identify a 30, 60, 90 triangle. In fact, I want you to work through this problem in which you know that this is a 90-degree triangle, 90 degrees, and this is a 60 degrees, and this is a 30 degrees, and you know that this is side 3. So I want you to figure out, now that you know the angles, I want you to figure out the two sides, and a problem right there. I want you to pause the video now that you don't know the sides, but you know that this is, the sides, but you don't know the angles. So I want you to figure out this side and these two angles, which is pretty obvious because this is a 30, 60, 90 triangle. So pause the video and identify that you know the 30, 60, 90 triangle. Familiarize yourself with it. So the next kind of special triangle is the 45, 45, 90 triangle. And this is an isosceles triangle. See, because these two angles are equal. And when two angles are equal, we know that two sides are also equal. So these two sides are equal. And when you see that there's a 90-degree triangle and one of the angles is 45, you can say, for a fact that the other angle will also be a 45. And when you know that these two excuse me, when you know that these two angles are equal, you also know that these two sides are equal. And find the third side, it is just under root 2a. I don't want to go into the proof of this. Sorry, it got deleted for a little bit. But okay, 45 under root 2a. I want to go into the proof of this, but it is very easy and you can figure it out using the Pythagoras' theorem. Okay, another formula that it will be really helpful for you in the SAT is the area of an equilateral triangle, and we'll do an example in a bit which will employ one of these formulas. And if you have an equilateral triangle, forgive my really bad drawing, I think I'll just use the one that I've used over here. And if in the problem you just you know the height of it, so you'll use this formula, and if you know the side of it, you can use this formula. Both of them are equivalent, and you can see if you can come up how did I come up with these formulas. Okay, last but not the least, with regards to the triangles, is the triangle inequality. The triangle inequality theorem states that for any triangle, the length of any side of the triangle must be less than the sum of the other two triangles, of the other two sides, and greater than the difference of the other two sides, which essentially just means this inequality. For a triangle with sides x, y, and z, I'll just draw a triangle here. If this is side x, this is side y, and this is side z, then we always know that the sum of any two sides will be greater than the third side, the length of all of these sides. This is important knowledge when solving problems that contain triangles. And here we have an example. If ABC is a triangle with AB, let's draw this. If AB is 5 centimeters and BC is 3 centimeters, what is the possible length of AC? So we know from the triangle inequality that the sum of two sides AB plus BC will always be greater than the length of AC. So AB is 5, BC is 3, then AC will be less than 8, basically. Right? This is something that we know from the triangle inequality, that this essentially just, if we flip it around, we just say that AC is less than 8 centimeters. Should be less than 10 centimeters. Nope. This is greater than 8. 8 centimeters. Nope. Because it should be strictly less than 8 centimeters. This is equal to 8 centimeters, which cannot be the case. 11 centimeters. Nope. It is greater than 8. Then 6 centimeters is the possible answer, and it is the correct answer. And now we move on to our next section, and this concludes our studies about the triangles. Okay, so our next topic is rather elementary and basic, and it is on congruent and similar figures. Here we see on the screen two pairs of triangles. One pair is a congruent pair and one is a similar pair. And this is the congruent pair. And the reason why I call it congruent is essentially these two are the same triangles. They're just rotated about some point. So it doesn't really matter. The thing that matters is these two are the same triangles. How do I know that? Because, well, I can just see that they're two, and they'll if on the SAT they are congruent figures, they'll tell you that these two triangles are congruent, which essentially means the corresponding sides will be equal, which means this is a 90-degree angle and this is a 90-degree angle. So this side, this side, this side, this side will be equal. This angle will be equal to this angle and this angle will be equal to this angle. Basically, it essentially means these are the same triangles, they're just rotated about some point. And you can even label the sides. This is side A, this is side B, this is side C. Then ABC corresponds to the side, wait a second, let me draw it a little better here. Sides B prime, sides C prime, and sides A prime, essentially. So these are congruent figures. Similarly, I shall label these points here. These are okay. These are sides A, B, C, A prime, B prime, C prime. Now, similar figures are essentially also the same figures, but they are resized. As in, when I say these are resized, but they are the same figures, what I mean to say is the ratios of the corresponding sides will be equal, which I mean, which essentially means that AB. So AB over BC for this triangle will be equal to A prime B prime over B prime C prime. So this is essentially all that is with regards to congruent and similar figures. And the different and a different way that I went about this topic was that I gave up the example straight ahead. So there's an example right from the SAT, and we'll employ this property of similar figures and work through this problem really easily. In the figure above, the right angle triangle PQR is similar to the right angle triangle XYZ with vertices PQR corresponding to vertices XYZ. So they've told you that the triangles are similar, which essentially makes it really easier. So if cosine R is 0.263, what is the value of the cosine Z? So cosine R, which means the cos of this angle equals, is just the base upon the hypotenuse, which is QR over RP. This is by definition of the cosine. Definition of cosine. Okay? This is cosine R. So what is the value of cosine Z? So they're asking the corresponding cosine of this angle. Okay, this angle, sorry. So we know these two triangles are similar, and we know that because these two triangles are similar, we know that QR over QP will equal YZ over ZX because similar. So cosine Z, okay, so we know this because the triangles are similar, and we know that the definition of cosine Z will be based upon hypotenuse, and which will just be YZ upon ZX. So, and we know these two ratios are are essentially equal. So cosine R will be equal to cosine Z. Okay, and cosine R was 0.263 from the question. So cosine Z will also be 0.263. Pause the video a little bit and try to understand what just happened here. And here's the solution to the example as well. So I've written down how I worked through this. So you can pause the video and have a go at it yourself. And this was entirely it with regards to congruent and similar figures. And next we have another topic. The next type of question that we'll be learning about today will be on quadrilaterals and polygons. Basically, quadrilaterals are any shape that connect 4 points in space. But there are many ways that you can connect 4 points in space in. So, for example, all four sides can be equal, two sides can be parallel, only one pair of sides can be parallel, so on and so forth. And we'll study about different types of quadrilaterals in a bit. And polygons are just, poly means many, and gons means sides. Excuse me. So, polygons are just shapes with several sides. For example, this is this is not a very good polygon. 1 2 3 4. How many sides does it have? 1 2 3 4 5. So it is a pentagon. It's a 5-sided polygon. So do not worry, you will not be asked about the names of these shapes on the SAT, but you should know what are the different types of quadrilaterals and polygons. So here I have summarized different types of quadrilaterals. And there are many different kinds of quadrilaterals, but all have several things in common. All of them have 4 sides. Quad means 4 and laterals means sides, basically. So all of them have 4 sides. They are coplanar because as in all 4 points exist on the same plane. Have 2 diagonals. Yes, they have 2 diagonals. These are 2 diagonals, and the sum of their 4 interior angles equals 360 degrees. So if this is a quadrilateral, for example, this parallelogram, so the sum of these 4 angles, these are interior angles, and sum of these 4 angles will always equal 360. So let's see and read about different types of quadrilaterals. So a parallelogram has 2 pairs of opposite has 2 parallel pairs of opposite sides. So these 2 pairs are parallel. So this is a parallelogram. A rectangle has 2 pairs of opposite sides that are parallel. So the rectangle also has a parallel 2 pairs of parallel sides, but all these 4 angles are 90 degrees. In a parallelogram, however, these 4 angles need not be 90 degrees. So this is the difference between a parallelogram and a rectangle. A square has 2 pairs of parallel sides. Yes, these 3 things are common in these figures. Both have all 3 of them have 2 pairs of parallel sides. But a square also has 90 degrees like a rectangle, and on top of that, all 4 sides are equal for a square. For a rectangle, only 2 sides are equal. These 2 sides are equal, and these 2 sides are equal. But for a square, all 4 sides are equal. And similarly, a rhombus is defined as a parallelogram with 4 equal sides, so the 4 sides are equal. But these angles need not be 90 degrees. So this is difference between parallelogram, rectangle, square, and a rhombus. And similarly, furthermore, what are trapezoids? Trapezoids only have 1 pair of parallel sides. So only these two lines are parallel to each other. These 2 are not parallel. So, and last but not the least, kites have 2 pairs of adjacent sides that are equal. So these 2 lines over here, they are equal, and these 2 lines over here, they are equal. So essentially, all the different types of quadrilaterals. Here I've summarized these properties in a bit more elaborated fashion, so you can read through them. I'd encourage you to pause the video and read all of these, and view the video again a little bit from before and see if you can make sense of this slide as well. Moving on. Polygons. There are 2 types of polygons, and we will be interested in mainly in one type, which is the regular polygons. And in the regular polygons, all sides are equal and all interior angles are equal. All angles concerned are actually equal, and I'll elaborate on this in a bit. Otherwise, it is irregular, and we can see an irregular polygon here, and this is just a regular pentagon. This is a polygon with 5 sides. Okay. So what are some properties of regular polygons? Okay, the sum of all exterior angles of a regular pentagon always add up to of a regular polygon will always add up to a 360. The interior angle and exterior angle are measured from the same line so that they add up to 180. So basically, interior angle is 180 minus exterior angle, and we have 2 formulas for the exterior angle and the interior angle, and we have a very nice example from which we'll study what these 2 formulas mean and how are they used. So n here is the number of sides of the polygon. And I'll tell you how do we measure these angles. Basically what we do is we just extend these lines a little bit. I'll zoom in a little, and this then becomes the interior angle, and this then becomes the exterior angle. So for the pentagon, a 5-sided polygon, what will be the measure of an interior angle? So we can just employ this formula here. An interior angle will be 5, because 5 sides for a pentagon, 180 over a 5, which is just equal to, I'll leave that as an exercise, and the exterior angle will also be 360 over a 5. So this is also an exercise for you to compute. For a regular pentagon, the interior angles and the exterior angles will always be the same. Will not be the same, essentially. No matter for every different regular pentagon, you will find the same interior angle and the same exterior angle. Now we move on to our last type of question, which will be on circles. And circles are really important. So without further ado, let's just dive into these shapes that look pretty. They look pretty elementary, but they have a lot going on. So let's dive into circles. So I'll just use this circle here that I've drawn to talk about different important things about a circle. So this point right in the middle, from which every other point is at a fixed distance, I haven't really drawn it really nicely, is the center of the circle. So this point O is the center of the circle. This length here, which remains the same from the center to the circumference, to the boundary of the circle, is called the radius. A line that goes from one point of the circle through the center and to the other side, and essentially which is 2 times the radius. 2 times the radius is the diameter. Moreover, this boundary has a special name. This boundary has a special name. It's called the circumference. Boundary of a circle is a circumference. Is called the circumference. Okay, if we are talking about a portion of a circle and not the entire circle in question, and not the entire circle. For example, we're talking about this part only, and here's an angle, some angle theta. So this portion of a circle is called a sector. Portion of a circle is a sector. The part of the boundary that forms a portion of the circle, this part here, is called the arc of a circle. Basically arc of this sector here. So this is a sector, the entire area is a sector, and the part of the boundary concerned is just the arc. And if the portion of the circle extends to cut the circle into half, basically this angle extends to 180, and we're talking about half of the circle, then this sector has a special name. It's called the semicircle. So if central angle, these angles are called central angles. If central angles measures 180 degrees, then sector is called a semicircle. Okay, moving on to make our life easier in the SAT. Okay, I have just summarized all of these points here, the certain important terms. And to make our lives easier in the SAT, I've summarized a bunch of formulas that we can use, and we'll use this circle over here to illustrate what these formulas actually mean. So lines in a circle, we're talking about lines in a circle. So let's just draw a circle over here so that we can effectively talk about all of these formulas. So we have the circle here, and what is a chord? A chord is okay, wait a second. A chord is any line that that joins 2 points. I'll use a different color. 2 points on the boundary. This is a chord. This is a chord here as well. So any 2 points on the boundary are joined by a chord. So this is a chord. What is a tangent? A tangent is a line that is outside the circle and it only touches the circle at one point. This is a tangent. This is a tangent. It is a very it's not so good, but you get the idea. Moreover, we have two different angles that are really important, and these are called the inscribed angle and there is a central angle. So let's see what they mean. These are important properties about the lines of different lines. So a chord, so what do they say? A perpendicular drop from the center, here's the center, I'll draw the center here, divides the chords into two equal parts. So if I drop a perpendicular line, which essentially means these angles are equal, then it divides the chord. These two angles are 90 degrees. Then this chord is divided into two equal lengths. So yeah, that is it. And for this as well. If I drop a perpendicular line such that these two angles are 90, then this chord is divided into halves. And for the tangent, the radius, this is the radius, is always perpendicular to a tangent where it hits the circle. So this angle is essentially 90. The angle that the tangent makes with the radius is 90 degrees. Moreover, there are two really important angles that we are to talk about, and to study these really important two angles, we'll have to draw a new circle. So here is a new circle. So we've got two different angles. One is called the inscribed angle and one is called the central angle. And the central angle is just, if I have the center over here and I make a sector with the radii, and the angle formed at the center is just called the central angle. And if I take these 2 points here and connect them to the circumference over there, oopsie daisy. Okay, so I've connected these 2 points here, and this is an angle formed on the circumference. So this is called the inscribed angle. So I'll label these here, inscribed angle, and this is the central angle. And two very important things very important properties about these two angles are, if these points are A and B, and I make another angle here, I'll use a different color. If I make another angle here using these two same points, the measure of these two angles will always be the same. And here it is written, angles formed by the same arc. The same arc means arc AB on the circumference of the circle are always equal. And there is another property here. Angles in a semicircle is always at 90 degrees, which essentially means if I were to divide the circle into a semicircle, and wait, I'll just use another different circle for this property. If this is the center and I divide the circle into two semicircles, then any angle that I make over here on the circumference will always be equal to 90 degrees. So that is the second part. And then there are some important formulas. The circumference of the circle is just 2 pi times the radius, and the length of an arc, the length of AB per se, will just be the central angle, which is just theta in this case, over 360 times the 2 pi r. So that will give you the length of the arc length. Okay. And what is the area of a circle? It's pi r squared. What is the area of a sector? What is this area? Oh, oops. What is this area? So this area is just the central angle made by the sector, which is again theta over 360 times the formula for the area of a circle. So that is that, and that is entirely it about circles as well. So if you know these properties, you are surely going to be, breezing through the questions on the SAT. And next we'll jump on to problems that employ all of what we've learned today. Now we jump on to the examples. For the first example for today, in fact the second example for today, is about polygons and congruent isosceles triangles. What do they mean? Isosceles means these two sides are equal. All of these triangles are congruent, means this is essentially, all of these are essentially the same triangles. They're essentially, all of them are the same, but they are just rotated a little bit. Rotated, this triangle is just this, rotated here a little bit, this is just rotated here a little bit, and so on and so forth. So what is the value of x? What is this angle, they ask us. So we see, because the angle in the middle, the angle about some point is always a 360, and it is divided into 9 equal parts. So the measure of one of these angles is just 45 degrees here. This is 45, right? Yep. No, this is 40 degrees. I'm sorry, it's 40 degrees. Okay, so this is going to be a 40 degrees, and because this triangle is an isosceles triangle, which means this angle also will be x degrees. So, and we recall from our lesson on triangles that the interior angles of a triangle are always, the sum of them is always equal to 180. So we get this, and we solve for x, and x is 70 degrees. And here's your answer. So it essentially took me only 45 or 50 seconds to work through this problem, and it also needs, and it also should take you 30 to 40 seconds as well to work through a problem like this on the SAT. So here's the solution to this for review. Okay, moving on. We've got another question that employs all techniques that we've learned about circles. So let's read through this and work through this as well. In the figure above, O is the center of the circle. Segment BC is tangent to the circle at B, which means this angle is a 90 degrees. We've learned that tangent makes a 90 degrees with the radius. This is radius. If OB equals AC equals C, which means OB is 6 centimeters, AC is also 6 centimeters, but OA is also the radius, so it also is 6 centimeters, which means OC is 12 centimeters. Now we see something fishy over here. We see OB, we see that OC is 2 times OB in a triangle. And remember that whenever one side of a triangle is 2 times this, whenever one side of a triangle is twice the other side of a triangle, and one angle is 90 degrees, then what triangle is it? It's a 30, 60, 90 triangle. So this angle in the middle is a 60 degree angle, and this is a 30 degree angle, and this makes our work pretty easier now. So now we can use our formula to calculate the area of this sector here, which was just the central angle divided by 360 times the formula for the area of the circle, which is just r squared, which is 36 squared. So this essentially means 1/6 of 36. This is essentially 6 pi. So the area of sector is 6 pi, and now we can just subtract this area of the sector from the area of the triangle. So the area of a 30, 60, 90 triangle is pretty easy to compute. It's just half times area of the triangle is half times base is just 6 into height, which is the height is just 12. So this just becomes oh no, am I doing something wrong? Yes, I am doing something wrong. This is not OC, is not the height of the triangle. In fact, this is the hypotenuse of the triangle. And for a 30, 60, 90 triangle, the hypotenuse, the adjacent side or the perpendicular side is just root 3 times the base. So it's 6 root 3. So this is just 3, and then the area of the triangle, the entire triangle, is 18 root 3. And the area of the shaded region here in the question, shaded region here, is just the area of the triangle minus the area of the sector of the circle, which is a 6 pi. So our answer is B. And here I've worked through the solution as well. So the area is 18 root 3 like we just got here. Oh, sorry. Okay, moving on. The last example for today. It is on parallelograms and trapezoids. So let's see what it reads. Trapezoid is a figure, remember, that only has one pair of parallel sides. So they ask us how much greater is the area of the trapezoid than the area of the parallelogram with sides with side lengths AB and base angles of measure 140 of measures 45 and 135. So for us to make this trapezoid a parallelogram, what we need to do is to have two pairs of parallel sides. Remember that a parallelogram has two pairs of parallel sides. So if x, y and w, z are already parallel, we need to make this line here such that sides, and I'll label this p, such that wx is parallel to py. And they say that the length that the measure of the base angles is 45. So this is 45, this is a 135. Now the figure WXPY is a parallelogram. So what do they ask us? They ask us how big is the trapezoid than the parallelogram. So if this is 135, this angle will be 180 minus 135 because they're on a straight line, which is just 45. And if these two angles are 45, and because the sum of the interior angles of a triangle is always 180, this angle must always be a 90 degrees. So now they ask us how much. So basically, the area that the parallelogram is smaller than the trapezoid is just the area of this triangle here. And this is a 45, 45, 90 triangle now. So it makes it very easy for us to compute the area of this triangle, which we can use the formula for. So because it's a 45, 45 triangle and this side is A, we know that this side also will be an A, because now this is a what? This is a parallelogram. So now that these two sides are A, and this is the base and this is the height of the triangle, we can just use the same old formula that we had in 8th grade about the area of the triangle. Forgive me, there's a mistake here. So the area is half A squared, and this is the area that the trapezoid differs from the parallelogram. So the trapezoid is the area of the trapezoid equals area of parallelogram minus half A squared. So that is essentially what it means. Here I have the solution to this problem. So if you want, you can read through this as well by pausing the video. And I hope that you've understood what we've done today. What we've essentially done is we've worked through different types of problems that you will be asked for in a geometry on the geometry section on the SAT. Where are the types of questions? So we worked through lines and angles, we worked through triangles and other polygons, we've worked through congruent and similar figures, quadrilaterals and polygons, and circles. I hope you understood everything, and if you did not, drop a comment below and I'll be sure to help you with that. Thank you and have a nice day.